Fine. Now let's look at another concept called the condition number, which is actually which is actually derived from what we have already seen related to the relative error, which is actually a compact way of representing a relative error. Okay. So we've already seen the relative error which we had, which is the norm of matrix norm of A inverse minus A plus B whole inverse divided by matrix norm of A inverse. It is less than or equal to norm of A inverse E minus norm of A inverse E, where we saw that it is where this matrix norm is A inverse E is less than 1. Fine. So we've already seen this. We've seen that the assumption was that the spectral radius of A inverse A is less than 1. Also, the norm of A inverse E is less than 1. So under these assumptions, we have derived the above expression. Now, by submultiplicativity, the norm of A inverse E will be again less than or equal to norm of A inverse into norm of E, matrix norm of E. So let's suppose that this value is also less than 1. We all know that this is A inverse E, norm of A inverse. We assume that an A inverse E is less than 1. Let's also assume that norm of A inverse E into norm of E is also less than 1. Oh, I think there is no here. This is a mistake. Interaction resist. Right. This is also less than 1. Then our expression will get slightly modified. So what we had, the relative error, norm of A inverse minus A plus C the whole inverse, norm of the matrix norm of that divided by matrix norm of A inverse will be less than or equal to. Instead of A inverse, norm of A inverse E, we have norm of A inverse into norm of A inverse E. Similarly, in the denominator also, we have 1 minus, instead of norm of A inverse E, we have norm of A inverse into norm of matrix norm of E. Okay, now we can take, since matrix norm is A is not equal to 0, so then matrix norm of A is not equal to 0. Then you can take matrix norm of A outside, so that we'll get matrix norm of A inverse into matrix norm of E into matrix norm of E divided by matrix norm of A in the numerator, and the denominator you'll get 1 minus matrix norm of A in inverse into matrix norm of A into matrix norm of E by matrix norm of A. So this particular term in the numerator and denominator, we define this as the condition number. So the condition number is defined like this. The condition number of a matrix A is defined as non-singular. Is A inverse and matrix norm of A inverse into matrix norm of A if A is non-singular, and if A is singular, it is defined as infinity. So always note that condition number of A is equal to norm of A inverse into norm of A. By submultiplicating, this is greater than equal to norm of A inverse A, which is equal to which is greater than, or the condition number will be greater than norm of I, which in fact is greater than 1. We've already seen the norm of I is greater than equal to 1 earlier based on submultiplicativity. So the condition number will be always a value which is greater than or equal to 1. So 1 is the lower bound of the condition number. So the above expression for relative error, which that can be modified as the condition number of A divided by 1 minus condition number of condition number into norm of E divided by norm of A, the whole into the norm of the error matrix divided by norm of A. So this is the expression for the relative error. So how will the condition number matter is, so suppose we have a small condition number which is approximately very close to 1. What happens is The numerator will be small. Also, the denominator is 1 minus s. The denominator will be large, and so the entire this fraction will become smaller. So even the error is not for a small change in measurement or for this perturbation. It is not amplified a lot. But if the k value is very large, then the numerator and this entire fraction will become very large. And even for small perturbations like E, the change relative error will actually blow up. So matrices which have a large condition number is an ill conditioned matrix, so which is not like very useful in some cases or very desirable. And if condition number is equal to 1, what will happen is the error will be 1 by less than or equal to 1 by 1 minus E by A. So that is the perfectly conditioned matrix which we can have, condition number 1. An example of a matrix with condition number 1 is if you have an operator norm, then I. Also, another property is if the product of two matrices is actually less than or equal to, I mean, the condition number for two matrices is actually equal to less than or equal to the product of their condition numbers. So this follows straightly from the submultiplicativity property. You just have to put the definition of the condition number here and do submultiplicativity. So these are some things which we want to know about the condition number.